So we're recording. I can see that, and let's go ahead and get going. So, first off, thank you all for showing up tonight. Like I said, this isn't mandatory. This isn't anything like that. For those of you who aren't part of the Buddha program, because I know there's some people from different programs who have the opportunity to take this class, the collaborate sessions are something we've been doing since we started the business data analytics program. So this is year 9 of that. And what these are online like lab sessions or online help sessions. So whether you all show up or not, I will shoot one of these every week of the class. Okay. What this is a chance for you to go interactive with me, ask questions. This is truly an asynchronous program. You don't have to be, you don't have to be at any of these things. This is a chance for you to, I will always be here at this time unless I'm not here, right? Unless I email you to say, hey, we're moving this because something happened. Just like you all, I have stuff outside of work and outside of school and outside of those things. So the one thing I want to tell you all, and it's something I think I've said in a video at some place, um, thank you all for doing this. Thank you all for, stepping up and growing and doing all of these things. I know you're doing this on top of something, and doing an online program's difficult to begin with, and taking an online stats class is really tough. The one thing I will tell you about the way I approach this, and let me be very clear about this, I view it as us against the material and what we're trying to accomplish. Okay. So this stuff's hard enough. I do my best not to make it any harder than it has to be. And that's what these sessions are about. These sessions are about getting really hands on with technology, getting really hands on with problems, getting really hands on with the data itself, and talking through why we're approaching problems in a way. In these sessions, we'll talk about what you should have learned last week. We'll talk about what you should have been thinking about as you came through the module. We'll talk about the upcoming homework. We'll talk about some things going on in the class. And then if anybody had any questions or anything like that, everybody has an opinion on how online programs should work. I'm very opinionated on mine. This is my 13th year doing online programs. Y'all, I'm getting old. That's what that comes down to. My gray hair is going to give me away at some point. But what it really comes down to is, you all work really, really hard at stuff. And I want to help you be successful. And this is one of the ways I try and help you be successful. As a professor, I pride myself in trying to run a student-centric course. And when I say try, I do try. I'm not perfect. So if y'all have anything you need, just ask. I'll do my best to help. I can't always promise I'll help immediately, because like I said, can't be perfect, but I'll do my best to help you in any way I can. So with that said, before I start sharing my screen and we get into anything, is there any questions anybody has? Again, these aren't required sessions. These aren't one of those things. We are recording. I will post this to the YouTube channel. That way you always have access to it. Any questions before we get rolling? Y'all gonna hear me say this a lot. Y'all good? I sound like an absolute hillbilly.
Good. I
Good.
do
Good.
have questions, but I'm sure they're gonna kind of like trickle along as we go through some stuff. So, um,
Perfect.
I'll have them.
Perfect. Awesome. All right, let's get rolling. So first things first, I'm gonna share my screen. Gonna ask that, amazing question that everybody always asks. Make sure we can see my screen.
Yep.
All right. All right, let me get you all set up on my second screen here so I can see everybody. Um, and then I'm gonna show the chat over here as well. All right, so you all can see R and R Studio, right? Real quick, by show of hands, how many people on the call had ever used R before I kind of said, hey, please download this for me? Okay, we've got one hand, two, three, cool, awesome. So I'm a big fan of R. I've been programming in R since 2005, 2006, which we're coming up on the 20th year of that. So yeah, showing my age a little bit there too. So I've been programming in R since I was 18. So I've been doing this a while. I've got packages that have about 1 million, 2 million downloads a year. Like we do some stuff in this, right? One of the things I will tell you, and one of the things I think is probably the coolest thing about R is you can do anything you want in it, right? R and Python both solve very similar problems. Python is built for more software engineering nowadays. One of the things I think is the biggest thing is R is built as a functional programming language. So I'm a true believer that if you can learn Microsoft Excel, you can learn R. And my goal is to help you learn it in a way that is functional for you. Okay. So what I've done for you, and I'll do this before every collaborate. And if I don't, you all hold me to it and say, Brad, you didn't do it. I can't find it. Post it. I have set up the collaborate document, and the collaborate document for tonight is an R Markdown file. You can click on collaborate module 1. So if you go into eCampus, all right, if you go into eCampus and eCampus Ultra, it's the new format, and I apologize about it all. And click on collaborate for module 1. It'll bring you to a R Markdown file. It'll bring you to this R Markdown file. Okay. If you just go here and click download raw file, you'll be able to pull it down from GitHub. Now, I want to explain a couple things to you because I try and be openly transparent with our students. I try and be as blunt as I can be with our students when it comes to these things. We are hosting on GitHub this year because Blackboard Ultra system is not built for the type of class we're going to run, and that's what the university's provided us. We like code, we like math. We're not scared of those things because we're going to engage with it. We're going to use it to problem solve. But the type of things we want to do, it's not set up for. And when we asked it to be set up for it, they smiled at us and went, wow, that sounds really interesting to teach online. And go, yeah, we've been teaching it on there for 10 years. And they go, wow, we didn't think about that. And I go, okay. So we've done this before. GitHub's a platform we're going to use to the point where in discussion 2, you and your teams are going to write about GitHub. That's going to be your position paper for module 2. Module 1's about p-values. Module 2's about GitHub because there's a history about GitHub I want you to know. And so you're going to write basically a page or 2-page position paper on GitHub and learn about its history because it's a really cool history to me. And Microsoft has a whole lot to do with it. But if you download the raw file, you can pull it. And if you click download the raw file, it can download it and you can open it in RStudio. Now, what you'll see is I've developed you another set of notes because not only do you have my notes, which are basically my personal notes. What you're going through every week in a module are my personal notes. And I'll give you a little bit about that as we go because I do want to spend some time talking about module 2 tonight. Okay. What you'll see is I've developed a document for you. Tonight, we'll talk about an example. We'll talk about why Bootstrap. We'll talk about some different things. We're also going to talk about how I want homework documents set up. We're going to talk about all these different things. And this document gets you a way I want homework documents set up. We'll get to that here in a second. All right. I don't want to move too fast. I don't want to go over things too quickly. One of the things I want you to understand is every collaborate, there will be a document. We'll be able to go through it together. You can watch me. Again, this is recorded. You will have access to that collaborate document. The collaborates are built to be extremely applied. They are going to seem very, very similar to something you may be doing later. Okay? The way I design my homeworks, I will never ask you to do anything without a purpose. Okay? I will never ask you to do anything without a purpose. So speaking of that, let's look at what you have to do for homework this week. Homework is due September 3rd, which last time I checked, that's a week from tomorrow. So, instructions. This module focuses on the intersection of statistical computing and statistical inference. For those of you all who have completed, and I think I looked because I can see who interacts with stuff, most of you have at least been in the module. Ideally, you would always write the optimal code, but that's not always possible. So let's explore some options. Morgantown's great. There's a lot of you'll hear it in videos. There's a lot of ambulances that go by my office. There's a lot of fire trucks that go by my office. So I do apologize about that. So if I ever hear a siren, I pause, okay? This is from the 1995 U.S. News and World Report data on 777 U.S. colleges and universities. Here's how you get to that data. This is the exact R code you need. Motivation from this problem comes from the idea we need to understand markets in which competitors operate. Colleges are no different. If you understand what's going on in higher education right now, you really understand there's competition happening. A bunch of universities are closing, a bunch of universities are transforming right now. Higher education institutions need to know how things change across different areas. In this assignment, we're going to mix exploring this data with practice in R a little bit more. This is a group assignment, meaning only one assignment needs to be submitted per group, but everyone should be familiar with the code that has been written. Attach the RMD and PDF or doc files, which means I want your R Markdown file and the resulting. You can use a Microsoft Word or you can use a PDF file. I don't care which. Why do you give me the R Markdown file? One is like showing your work on a math test. If you show me your work, I can give you partial credit. I'm a huge partial credit fan. If you get one piece of code wrong, but the logic is right, that's a huge piece of partial credit because I can help you fix the logic, right? If you get all the code right and part of your explanation is wrong that I ask you for, that's a huge piece of partial credit. But if you just show me the explanation and no code, you're not going to get very much from me. I need to see the thinking. Part of this class is learning to problem solve with data and technology. I need to see the full workflow. Okay? Now, problem one, run a bootstrap confidence interval for the apps variable in the college data set. This is the number of applications that are received. Using 1,000 bootstrap samples, calculate the 80% confidence interval for the mean number of applications each school receives. Pick one of these three methods to use. You only need to use one. Do not use all three. Store the mean of each bootstrap sample without storing the data, just as in your notes. Store each bootstrap sample in a matrix and then calculate the mean of all samples have been taken using the apply function. Store each bootstrap sample in a list and then calculate the mean after all samples have been taken using sapply. These are methods we've talked about working in that you could do using your notes. Interpret the 80% confidence interval that you calculated. Discuss your choice of implementation of the three possible. Tell me what you did. Tell me how you did it. But the most important thing is interpret the 80% confidence interval. Okay? I'll zoom in here a little bit. Building on problem one, take your preferred method and calculate the intervals using 3 different random seeds. You used one in problem one, so you need to use 2 more. See how sensitive the result is to the random number generator. In other words, if we change the random number generator associated with the sampling, how much do our results change? After this, you will have 3 intervals with 1,000 bootstrap samples. Using the same 3 seeds and methodology, calculate intervals using 5,000 bootstrap samples. Report the resulting intervals. Comment on the results and the computational time. Hint, to change from 1,000 to 5,000, you can just copy and paste the code and adjust the number of bootstrap replications. You can copy and paste a lot of this code. That is my other hint. Once you have your code set up, copy and paste will be your friend. You're just changing certain numbers, okay? Write one good piece of code and you can copy and paste a lot of it. All right? Next piece. In the same problem, or in the same college data, we have the private variable, which is an indicator of whether schools are private or public. Use a randomization test, randomized distributions, to test the statement, public schools have more application than private schools. You may choose the statistic you use for comparison. I suggest the mean or the median. For instance, the mean number of applications for public schools is more than the mean number of applications for private schools. Pick a reasonable significance level and state your results. Comment on the data size. Are 777 data points enough to make any conclusions? Defend your statement. Notice what I'm asking you to do. Notice I'm asking you to code it, but also explain it and give me justifications. It's not enough, what you'll figure out with me in my classes, it's not enough just to run code for me. You've got to tell me what's happening. We live in a world of AI now, right? Cool. You get AI assisted code, and I even told you in my syllabus, use Gen AI if you want. You got to tell me what's going on after the fact. You've got to draw the conclusion with me. You've got to tell me the next step. You've got to defend what you did. And so when we talk about these things, that's the win. Again, this is a group assignment. Your groups are in eCampus. Tell me if you have any questions about that. Work with your group. This is one of those things. This is a team game. Data analytics, AI, data science, whatever you're calling yourself to get paid right now. And that's what I suggest you do, right? Is a team game. You work on teams. You work on cross-functional teams. Treat it this way as well. Treat it this way as well. Any question about the homework? This is not due until September 3rd. You have over a week from tonight. Okay? Any question about this?
Nope, I'm good.
Brad, could you just link to that page if you can into the chat?
Yeah, it's on eCampus. So unless you're up, it's homework 1 right here under module 1. So the problem with me trying to link it into the chat is the link won't live unless you're signed in. Let me see if it'll take me there for you. See if it works. It's the first time I've ever tried it.
No, it's all good. Found it. Just never used any of it. So
Okay. Here, we'll give it a shot, see if it works. All right. Everybody else good? Before we move on, going once, going twice. All right, so let's pull up the Collaborate 1 document. Again, you can find it here. It's at the bottom. It's at the bottom. It is visible to students. I have to double check. It is visible to students, and we're going to go through it. Okay. Now, you'll notice it is set up as an HTML document. It is set up to everything. If you ever run into problems with a document, the thing I want you to do is I want you to take your R Markdown document and I want you to email me your document. Brad, I'm struggling with code. Cool. Email it to me. Email me your R Markdown document. I've told you I've been doing this a long time. I have zero problem helping you learn. I have zero problem helping you figure something out as long as I can see you're trying. Everybody has had help along the way. That's the thing I need you to understand. I had a ton of help. My advisors, the people who helped me, had a ton of help. Nobody has ever done this alone. So the last thing I ever want you to feel is alone. Okay? So if you're working on this 10, 20, 30 minutes and you're like, I can't figure this out, ask your group. Drop me an email. Hey, Brad, can you take a look at this? Sure, happy to. Don't expect me to respond in 5 minutes. Okay? I got a 7 and 10-year-old. I got stuff too. But when I see it, I'll jump on there. I'll respond as quick as I can. If you don't hear from me in like a day, ping me again. Hey, Brad, can I get some help? That means I completely missed it in my inbox. I swung, I missed. That's my fault. Okay? I am better than that. I promise you. And if I miss like that, that is my fault. If I haven't responded in 24 hours and it's a weekday, it just slipped through the cracks of my inbox. I get a lot of emails every day, but it is my fault I missed it. I try and respond fairly quickly. You know, if you email me at midnight, I'm not answering at midnight. I promise you that. But I'll get to it in the morning, okay? But if I haven't responded in a day, yeah, don't feel bad about emailing me again, okay? But please send me the R Markdown document. If you send me the R Markdown document, what I'll do is I'll fix it in the R Markdown document and I'll show you exactly what I fixed so you can see the changes, okay? Don't be scared to say, hey, Brad, can we jump on Zoom and talk as well? Happy to do that too. All right, so let's talk about this Collaborate document. So what I'm going to do is I'm going to open this up and I'm going to hit knit. That way we can talk about it in 2 ways. I'm going to talk to you about it in the RMD. I'm going to talk to you about it in the code, and I'm also going to talk to you about it in the document itself, okay? Now, I'm not going to read it word for word in the document because I assume we can all read it. But basically what this says, basically what the top of it says, up to this point, we've only discussed averages in Bootstrap because averages are the easiest thing to talk about when I'm introducing stuff to y'all. And I'm looking at this screen. It looks like my head's not talking to my camera because I've got you all on this, okay? So I'm checking out the chat. I'm looking at your videos. But basically what we're saying, and basically what we're talking about is we've only talked about means because means are the easiest thing for people to understand. People like to think they understand averages. People like to think they understand those things. But there are other statistical quantities we use a ton. We use medians. We use 75th percentiles. What you'll see is we use regression coefficients. We can bootstrap any statistical quantity. But the reason we bootstrap is we don't want to memorize equations. If I were to ask you all right now to give me the equation for a t statistic and tell me how to estimate every one of those quantities, back from your intro stat class, less than 25% of you could do it correctly right on the spot. And I would probably bet dinner that it would be less than that. Right? Because it's been a while. But if we went back and we talked about bootstrap and we showed everybody how to bootstrap from the beginning, what bootstrap is a way of thinking. It's a statistical methodology. It says, if we think about what statistics actually means, this goes to fundamental concepts. It says we don't have to memorize equations, we memorize a process. And that process gets us to a problem-solving framework. That's why I like bootstrap. That's why I like randomized distribution, because it goes back to fundamentals. It helps us learn code. That's the whole point of it. But what it does for us, and this is the method to my madness thing, right? It allows us to teach you code. It allows us to teach you those things. But what it does, it reminds you of fundamental concepts of statistics. It allows us to get to sampling distributions. So let's talk about a quantile for a second. Remember what a quantile is? It says this percentage of the data falls below this point, right? If I remember what a sampling distribution is, and we talked about sampling distributions in the module, so I'm not going to really remind you, but it's the distribution of the statistic. It says if I replicate my sample day after day after day or time after time after time, the statistic will follow this distribution. Well, the quantile, just like the mean, has a central limit theorem. And here's the central limit theorem. It says the sampling distribution for the sample quantile follows a normal distribution with mean exactly what you think it should be. So if you would do the median, right? The sampling distribution for the median would be the sample median and follow this distribution. The pth quantile times 1 minus p divided by n times this quantity right here, where this follows a probability density or mass function that you have to know. So you have to know what your data follows. You have to say it follows a normal distribution or a gamma distribution or all these things. That's a huge assumption, because I'll tell you right now, no data actually follows a named distribution. I'm a PhD statistician. No data actually follows a named distribution. We assume it does, but that's not how the world works. We make assumptions about how data works because it's a simplifying assumption. This assumption that we would say our data follows a normal distribution or our data follows this distribution, it doesn't work that way. Statistics follow a distribution. We have that theory, but data itself doesn't. All right? When we observe when we observe returns on a stock market, when we observe lead times of a product, when we observe revenue from a company, it doesn't follow a normal distribution. The averages of those things do. That's what a central limit theorem tells us. The quantiles of those things do. That's what this central limit theorem tells us. But the data itself, the raw data, does not. So making the assumption that that data follows a normal distribution is a huge thing. So we can't estimate this quantity, which means no matter what happens, I can't tell you what the variance is. So I can't do confidence intervals. I can't do hypothesis testing on the quantile itself. So I can't do hypothesis testings on the median. So even if the data would have outliers to it and the median is a better estimate than the mean, I can't do anything. So why do we bootstrap? Because it lets us do inference on quantities and it lets us do confidence intervals on quantities when we don't know how to do the calculations. The reason we call it bootstrap is the person who came up with it, his name is Brad Efron. He said, when you don't know what to do, it allows you to pick yourself up by the bootstraps and do something. All right? That's the phrasing we use. All right? So You don't have to make an assumption about your data. That's one of your big takeaways, and it allows you to do something. So, why do you bootstrap? Because you don't have to remember equations and you don't have to assume anything about your data. All right. Now, what we're going to do, we're going to work a little bit with the data you're doing on your homework. Okay. And we're going to take a look just a little bit at what's going on in that data. So the first thing first, I'm going to load up the ISLR package. So if I load up the ISLR package, remember, I can click on the line, and for me, I can hit Command Enter on mine. If you want to see what you can hit to run the line of code, you can come up here to Run, and you can see Run Selected Lines. For me, I'm on a Mac, so I can hit Command Enter. Okay? I can hit Command Enter. Whatever this shortcut is right here, we'll tell you what your keyboard shortcut is, and I use my keyboard shortcut. Okay? So this is ISLR, and you can, I'm going to load up college. If I look at the dimension of college, you'll see it's 777 data points and 18 variables. Now, I'm going to create some shorthand stuff here. All right, I'm going to create some shorthand stuff here. And we're going to do this a little bit of a different way than I already have this saved. Okay? We're going to talk about a few different ways to have this saved. And there's a bunch of different ways we can do this. Okay? Now, I'm going to do this shorthand, and what I mean by shorthand, I'm going to save apps as college $apps. Okay? Why do I want to save this as college $apps? Just so I don't have to keep writing this over and over. So remember in R, if I look at head college, what is this going to do? It's going to give me the first 6 rows and show me what my data looks like. So this data set is fairly large. It has the private variable, it has the apps variable, it has the number of accepted students, the number of students that enrolled. So think about this as a pipeline at a college. Here's the number of people that applied. Here's the number of people that were accepted. Here's the number of people that enrolled. So the top people that applied that were in the top 10% of their class, top 25%, full-time undergrad enrollment, part-time undergrad enrollment, out-of-state tuition, room and board, books, personnel employed, percent with a PhD, percent with terminal degrees, student-faculty ratio. Here's a measurement of alum expenditures, and then their graduation rate. Okay. Now, here's the shorthand. So we said I want to do college $apps. This is just so I don't have to keep writing this over and over. So what does this do? This gives me the college data set. $ is what we call the atomic vector. It says go to the college data set and return the apps variable. And I'm just going to save it as apps. This is the assignment operator, so it allows me to save it. Right? So what are we doing? We're saving apps. All right? Now, just as a reminder, this is my R Markdown document up here. To get it to execute, it must come down here to the console in the terminal. So see how everything, I just ran this line, and it now appears down here in the console. It has to execute down there. Just because I type it up here doesn't mean it's actually executed, okay? Now, we're going to do Bootstrap. So what's the whole point of the Bootstrap? The whole point of the Bootstrap, what we're going to do is we're going to bootstrap the median of the number of applications, okay? We're going to bootstrap the median of the number of applications, not the mean, but the median of number of applications, to see what the confidence interval for the number of the median number of applications is at colleges. Now, what we want to look at and what we want to think is, how do we do that? Well, what we do is we think about the process we learned in Module 1. What's the point of the bootstrap? We take the sample, we treat it as the population. How do we create a sampling distribution? We go in, we take a sample, we calculate the statistic we care about. In our case, it's the median, right? All right, we take that calculation, set it to the side, put all the data back. Go in, we take the sample. We're sampling with replacement. Why are we sampling with replacement? So it mixes the data up. So every time we go in and sample, we're not just getting the same numbers over and over again. We do this 1,000 times, 5,000 times, 10,000 times. So we get enough numbers to create a full distribution. And then we go through and we treat that as our sampling distribution. We have statistical theory that says this is unbiased. This will give us good estimates. All of these things. All the math works out in the long run. But what we're doing is we're treating the sample like the population, okay? To do that, we have to set a random number generator. That's what setSeed does. It points someplace in the random number generator and says start here. All setInTheSeed does is it says I can replicate this random number generator at the starting point, okay? Now, there's a couple different things we can do, and I've showed you 2 different ways to do this in your module. I'm going to show you the old school way, which is what's currently here, and then I'm going to show you the new school way, which is using dplyr, all right? Which is using dplyr. That way you can see it. So what we're going to do is we got to have a placeholder, okay? We've got to have a placeholder for how this works. So one of the ways to do that is to set up just basically an empty vector. So by setting up an empty vector, we're just setting up a placeholder. We're saying boots app equals null. All we're doing is setting up something empty for storage here. So by saying boots app equals null, all you're doing is saying, hey, create this thing called boots app and set it equal to something empty. So if I come down here, don't do this. It's saying this thing is empty. In R, null means empty. It means there's nothing in it, okay? Now, we're going to run a for loop. We're going to say for j in 1 to 10,000 because I want to repeat this process 10,000 times. I've written this in the most complicated way humanly possible because I've written it in the most efficient way possible. But let's write it in a less efficient way. Let's step through it just for 1 second here. So what I'm going to do is I'm going to write it using dplyr just to show you the difference. So I'm going to say library, dplyr. All right. And what dplyr does is it allows me to use piping and tidyverse. Okay. So I'm going to say apps. All right. What are we going to do with apps? We're going to sample apps, length, replace equals true, and then we're going to take the median. And I'm going to call this my samp. Okay. Now, I'm going to say boots app, C, boots app, my samp. Now, I'm going to walk you through these 2 lines and tell you these 2 lines are equivalent to this line right here. Lines 34 and 35 are equivalent to 36. Now, let me walk you through this. What piping does, what this does, what percent greater than percent does, is it takes what is in front and pushes it through to what's next. So I'm taking apps and everything to the right of it goes where the period is. So what we're going to do is we're going to sample apps with length apps with replacement. So what it's going to do is it's going to sample apps of size apps. So sample apps of size 777. Return a sample of applications of size 777 because that's how big apps is with replacement. That's the bootstrap sample. This right here creates the bootstrap sample. All right. Then take that and calculate the median of that sample. Save that result as my samp. Once you do that, come down here and say boots app concatenate. What that means is keep together the current state of boots app and add my samp to the end of it. All right. So what I'm going to do is I'm going to walk you through this twice. So I'm going to set my seed at 1900. I'm going to set bootstrap equal to null. So here's my SAMP. And I'm going to look at bootstrap. Let's see what bootstrap is now. Let me see if I ran this right. Bootstrap is 1470. Okay. So that's after I run it once. Let's see what happens if I run it again, because the for loop would just come through here and it would run it again. Now, here's my 1470. Excuse me. Let's run my SAMP now. Should be something different than 1470. This time it's 1576. All right. Let's run it a third time, because this would run 10,000 times if I let it. So here's bootstrap. 1576 again. Let's see if it'll do it again. This time's 1558. So you see what's getting ready to happen. It's getting ready to repeat this over and over again. All right, so what we're going to do, we're going to let it run clear through, and we're going to take the histogram. So it's going to run 10,000 times. And here's the histogram. So what do you see? Does that look like a normal distribution?
No.
It's not a normal distribution. So the first thing we can see based on this is that doesn't look like a normal. There's something weird going on in the data. Now, if we increase the sample size, it would be normal. This theory works, but it says as your sample size increases, it works. With this data, there's something going on here that won't allow it. What you have to remember is medians are discrete. Medians are discrete. Quantiles are discrete. It will pick up in the middle. So these things have to replicate this way. So we could calculate the confidence interval just like we talked about. Just like we talked about in the module. You calculate the quantiles off of this. If I wanted to calculate the 80% quantile, right? I put 10% in the lower bound and I put 10% in the upper bound. Right? Or 10% in the lower tail and 10% in the upper tail. The way to do that, there's your 80% quantile, because 80% is contained between those two numbers. How am I getting 80% is in between those two numbers? What's 90 minus 10? 80. That means 10% is below that, 10% is above that, right? That's the definition of quantiles. All right. Now, just to walk you through how we would do a matrix here. You could do it this way with multiple seeds. All right. And I'm not going to take you through a ton of this because I want to do the hypothesis test on the last one. But this would be how you would do it for a matrix. You can save it as a column, which is what I do right here. And then you can save it as a list. And you can see exactly what I'm doing. I'm just sampling. I sample, and then I calculate after the fact, okay? Now, these two examples right here, you'll see I'm using the apply function, all right? You'll see I'm using the apply function. Now, I do want to introduce you to this data. So we're going to take a look at this wage data for a second. This wage data is the Mid-Atlantic wage data. So wage data and other data for a group of 3,000 male workers in the Mid-Atlantic region. This has year, age of the worker, the marital status of the worker, which we're not going to get into tonight, the race, the education, the region. They're only from the Mid-Atlantic. They have a job class, whether they were industrial or information workers, the health status, their health insurance, and then their log wage or their wage. We'll use this data set a bunch on Collaborates throughout the semester. But basically, what we do through this process, and I'll run through this top one with you just to show what I'm going to do here, is I'm going to replicate what we just did. Here, notice I didn't store the samples. I just calculated the median directly, right? I ran the data and calculated the median. But I can always get back to that data because I stored the seed, right? I can make this audit proof. I can make this replicable. I can make this a repeatable study, right? Reproducibility is high in this study. It's something that's very, very easy to do and come back with. So what we're looking at and what we're thinking about now is, how do we do this if I actually need to store the data? If somebody would need me to export every simulation I had for some type of audit, for some type of compliance, how would I do that? This is something that comes up, and I'll show you one of these examples. I could store it in a matrix or I could store it in a list, and I'll just show you the matrix version of it because the list follows pretty simple. I'm going to look at the wage variable. So, show you a summary of wage. Here's what it looks like just so you can see it. I have the year. I have everything from 2003 to 2009. I have the age starting at 18. Somebody's still working at 80. I have the distribution of marital status, never married, married, widowed, divorced, separated. Here's your race distribution. Here's your education distribution. But you can come down here and look at wage and see everybody. And these are workers' raw wage. Everything from 20 to 318. All right. And these are standardized wages. It doesn't give us the breakdown of what values they're in. So the one thing I do want to show you here is the histogram of wage. And so we'll come down here and let's look at the histogram of wage. What's the first thing you see about this histogram? My first question to you, is that a normal distribution?
No, it's got a long right tail with some outliers.
So does that concern you all?
Yes.
So when you look at a distribution like this, the first thing that goes up are like flags, right? Like I got a problem here. This looks nice and stable, but there's still a little bit of a skew going on here, right? That still doesn't look completely normal. All right. This out here still has some weird stuff going on. So we need to figure out what's going on with that. But let's go ahead and see what the average salary for these workers are to begin with. So we're going to set our seed, and then I'm going to store this in a matrix. Now, what I'm going to do is I'm going to initialize a matrix with 3,000 rows and 10,000 columns, because I'm going to do 10,000 replications, and I'm going to store every sample in a column. Why? Because that's what I've decided to do. I'm making a plan before I do this. I'm going to do 10,000 replications. Why? Because that's what I've decided to do. As long as I'm doing enough replications, it'll work. All right. Do 1,000, 5,000, 10,000, right? Like that's what I'm deciding to do. I'm going to store it in the columns. I'm storing my replications in the columns. So I need 3,000 I need 3,000 rows because that's how many observations I have. So I'm calling what I'm storing it in store because I'm creative, right? What you'll figure out is statisticians are the least creative people on the planet. We name things really, really simple. All right. So all I'm going to say is for I in 1 to 10,000, store, the ith column of store is just sample wage, 3,000 times replace equals true. Create the bootstrap sample and put it in the ith column of store. So let's do that. All right, it's done. Now, I'm going to use my apply function. What's apply? Apply just says take this function, apply it to the columns or rows of whatever this matrix is. So I can apply it. If it's a 1, it's the rows. If it's 2s, it's the columns. I want to take the mean of the columns of store. That's going to give me my bootstrap sampling distribution. So that's going to give me my bootstrap sampling distribution of the mean. So I can call that boots. And then here's my histogram of that. Is that normal?
Yes. Looks better.
Looks a lot better. So that is the distribution of the mean of the wage data. That meets every statistical theory we've ever seen. We can do everything we want to do. We can do quantiles. We can do statistical inference. We can do everything we want. Okay? This is just another way to do this. We just save the columns. It's there. No trick. What makes this work and what made that look normal was I calculated a mean instead of a median this time. Okay? If you would come up here and change this to a mean, kind of like what I'm asking you to do in your homework, it'll work for you. Okay? All right. And again, this is what happens if you change your seed. This would be what it would look like if you would change your seed and run it, like I'm asking you to do in your homework. So if I would copy and paste the code I just ran and did it. All right. Now, here's the list example. If you want to try it, all I'm doing is taking that same code and storing it into a list this time. All right, in 10,000. Now, there are reasons we don't do this. It's the opportunity to do it, but there's a reason we don't. It's storage. If you look at the notes and if you listen to these things, if you listen to me talk in the videos, because I know I talk a lot in the videos, I know there's a whole lot of videos, but I try and make sure you all have it because I know reading notes is hard. I don't like, there might be there's a couple people in this program who've had me for another classes or classes throughout undergrad. I don't assign readings. I don't like assigning readings in books. I'd rather lecture, right? Part of that is because I want you to hear it from somebody. And so it's how it all works. So you can do it that way. The other thing I'll show you, so you can use this on your homework, and this is a piece of advice. If I wanted to calculate how long something took to run in R, there's something called sys time. So on line 96, sys.time tells me how something started. Mine 2 is sys.time. If I look at the difference between mine 2 and mine, it tells me it was 8 seconds. So if I would run this, it would tell me how long it took from line 96 to line 101. So if I would highlight that and run it, it would tell me how long it took. There's other ways to do it, but that's a real crude way. Okay. All right. Last thing I want to touch on tonight. I want to look at the difference between job classes because this job class has industrial and information workers. And with what we're all here studying, we hope that information workers make more than industrial workers right now. We hope we're making a good investment of our time. So I'm going to run t-apply, which is something we talk about in the notes. I want to look at the mean of wage by job class. That's what t-apply allows me to do. So let me look at this and let me see what mClass does. It allows me to look at the difference between information and industrial workers. Information workers have an average salary of 120, while industrial workers have an average salary of 103. Boom, we're done. Information workers make more than industrial workers. Great, no statistician ever needs a job again. We're done. We're going to call it good. So we better put some statistical inference on this just to see. So what we're going to do, we're going to say is, can we say with confidence that information workers make more than industrial workers? How do we do that? We're going to do it using randomized distributions. So I'm going to calculate my test statistic, which is information minus industrial. I want to say information workers make more than industrial workers. That's what I want to be able to say. My test statistic The data I observed is positive 17. All right. It is positive 17. The data we observed said industrial or information workers make 17, I think it's $1,000 on average more than industrial workers, which is a great number for us. We want to say that on average, info workers make more than industrial workers. Since we're saying it's greater, that's an alternative hypothesis. It doesn't have an equal sign. The null hypothesis is the equality, right? So we want to generate data under the null hypothesis. It just says the two things are same. So what we can do is we can just randomize the information assignment, or we can randomize the assignment of the salaries. One of the two. Either way, it's going to do the same thing. We just want to mix up the data and create a sampling distribution under this null hypothesis to see what would the possible distribution look like, and then say, could our data have come from that? Could our test statistic have come from that? It's legitimately that easy to test hypotheses. We teach you all these other test statistics. We teach you all how to do all this other stuff. But really, if you could generate the sampling distribution under the null hypothesis, it's pretty easy. All right, so let's set our seed. Let's create this. Now, what we're going to do is I'm just going to randomly assign the job class for 300 people. I'm going to sample without replacement. So what it's going to do is it's just going to mix up the job class over and over and over and over and over. Okay? I'm going to create a new data frame with the same wage and just a mixed up job class. I'm going to calculate the differences, or I'm going to calculate the mean for each one of the new job classes. And then I'm going to calculate the difference just like we just did. So if you look at this, here's what I'm getting ready to do. This is my new data frame. This is my mean for my new job classes, which tells me information just makes slightly less than industrial. In an ideal world, they're exactly the same, but I'm sampling from a world where it's mixed up and they should be random. They should be equivalent. There should be no effect of information or industrial, right? And then all I'm going to do is I'm going to calculate this difference, which is information minus industrial. Yeah. I'm going to calculate this difference and save it. This thing should center right around 0 if I do it right. So let's see. It's running because I'm trying to run it 10,000 times. All right. Now let's see if I did it right. There's my distribution. That's the distribution under there is no difference between information and industrial workers. So that is the null distribution. Does that look like the correct distribution if I would say there is no difference between information and industrial workers? To me, it does, because there's a 0 there. By the assumption, I'm looking at the statistic, information minus industrial. If I'm saying that's the distribution where there's no difference, it should be centered at 0. And that's centered at 0. Does everybody agree with me? Does everybody agree with me that's centered at 0 right there?
Yes.
Yes.
So that would mean that I got that distribution right. Okay? So we take a step back. All right. Now let's see where my test statistic goes. Now, if you're running this in an R Markdown document, I want to show you this is going to crash. See how it yelled at me and it said, no, you didn't have it. Anytime we try and put a line on a plot, which is what AB line is going to do, we've got to call the plot and the line at the same time. AB line V equals my stat. What it's going to do is it's going to put a vertical line at our test statistic. And remember, our test statistic, we calculated up here. That's the test statistic from our data. That's from the original data, okay? So it's going to put it at 17. Now, this is the easiest question I've ever asked you. And I've asked y'all a lot of questions between all the videos and everything else. And I've asked you some questions tonight, and I appreciate y'all responding to me. Makes this a whole lot more fun. Does it look like that black line came from that distribution?
No.
So this is how easy hypothesis testing is. If that black line couldn't come from that distribution, do you reject or fail to reject the null hypothesis?
We reject the null.
You reject the null. That's really what a hypothesis is asking, is could your data come from that distribution? If the answer is no, you reject the null. It's not reasonable for you to say my data came from that distribution. That's all a hypothesis test is, y'all. It's really that simple. Let me show you. The p-value, what it's asking, is it saying, did my data, is there anything in that sampling distribution greater than or equal to my statistic? And if there is, sum it up and divide it by 10,000. This right here will say, give me the proportion of times in my sampling, in my randomized distribution, my randomized sampling distribution, that I observed a test statistic greater than my statistic. The answer is 0. So if I run all this at the same time, just so you can see the picture and everything, you'll see the 0 and you'll verify it here, right? There are 0 times it showed up there. There are 0 times it showed up there. All right. There are 0 times it showed up there. So giving you a couple examples of how to bootstrap tonight. If I had to give you one recommendation, I would bootstrap this way. There's a reason I show you this way in your notes. There's a reason I focused on it this much tonight. If you want to mess around with R programming and get good with lists and you want to get good with matrices, you can do it the other ways. But this is what I suggest. One, it's easily accessible, but two, from a storage perspective, because we think about cost, we think about those type of things from a business perspective, this is the cheapest way. It's fully reproducible, so it's audit proof as well. And unless you're in a highly compliant environment where people need you to export all this data, and at this point, it's super, super rare. I can think of 2 industries, and both of them are highly FDA regulated, and the FDA is even supposed to be moving away from some of that. This is fine for you. So if you're asking me what I would recommend on your homework, especially if you're new to R, this, okay? Lower barrier to entry, those type of things. If you're trying to show off, you can try these too. And I don't mean that in a bad way. Like if you want to dig in, all right? And I'm happy to help you with either of them. Like I will never look at you and be like, you shouldn't have done that. And I won't take off points because I thought you tried something too hard. Like I'm all for you growing. That's part of what these programs are for. That's part of the reason I give you the 3 options. But remember, this is a group assignment, right? So think through those type of things. And again, if you notice what I did here to show you how you would change your seed, this is a copy and paste of my stuff above. I've told you how long I've been programming. That's not to show off. That was to set a tone for you. I copy and paste my own code, right? I use my own code and I copy and paste to do those type of things. All right. Brooke, you asked a question. I didn't mean to ignore it. You're talking about, let me finish up what I was talking about and I'll come back to your question. The last thing we talked about was the randomized distribution. Randomized distributions are really, really important. They basically allow us to do hypothesis testing in an environment that really mimics the bootstrap. But it allows you to get to think critically about what is the problem. It allows you to think about p-values in a way that allows you to facilitate decision making, at least to me. It allows you to look at things like this to go, can that data really come from here? Is it reasonable for me to make a decision this way? Is it reasonable for me to reject the null hypothesis or whatever the null hypothesis means to me in my decision-making paradigm, right? So it allows me to think that way. So with that said, if you need help with your homework, let me know. Brooke, coming over to your question. So Brooke's question's in the chat. Can you explain why the first histogram is not good? I was thinking it looked decent because the data was concentrated and the concentrated data, the IQR. Are we paying attention to the outliers? Are the outliers part of the clean data? So, Brooke, when you were talking about that, are you talking about the wage data or are you talking about the bootstrap that we did with the median?
At this point, I don't remember, but I know we were looking at the histogram that was rate skewed and then bell-shaped.
So you're talking about this one.
Yes.
So there's nothing wrong with this. So when I tell you there's nothing wrong with this, it's just not normal, right? It's not bad. It's just the histogram of the data, right? So when I look at histograms of the data, there's some stuff we'll come back to and we'll work with this a ton. There's nothing wrong with data like this. Actually, we love data like this. When we see data like this, by the time we get to module 3, you all are going to know I know exactly how to deal with this. Okay.
Okay,
Um,
perfect. Yeah, I was just watching your video, so then I was a little bit confused, and I thought that the preference was to be bell-shaped over rate skewed necessarily, but yeah, you answered my question.
no, the preference is to be bell shaped when we get to the mean, like when we get to the statistic part. So after we bootstrap, we want it to be bell shaped.
Okay, okay, thank you.
Yeah. If not, that's where we get to here. Once we get to this part, after we've done the bootstrap, that's part of the reason you'll see me use the quantile statement because it's always robust to that, right? So in the videos and in the module, you'll see me say you can do mean plus 2 times standard error, right? Or you can use the quantile statement. There's a reason I always default to the quantile statement is because it's robust to whatever the shape is. It's
Okay,
robust.
perfect. Thank you.
Yep.
I had a
All right.
follow-up question to
Yep.
that. So looking at outliers beforehand versus after, like how much is weeding out your outliers and doing like the quantile approach before you run your bootstrap versus kind of building it into the end? I feel like it's probably just an extra step and maybe overkill, but how important is that?
So the justification I want you all to give at this point, and we'll get into this later in the semester, the justification I want you to give at this point is if you're going to throw away data, you better have a really good reason to basically say, hey, I dropped it below this because for certain things, this just didn't make sense to me, right? Like if we're talking about, think about the Atlanta commute times example, right? Um, the Atlanta commute times example, one of the things we did was we filtered out anything over a 90-minute commute time just because I looked at it, I was like, who's commuting more than 90 minutes a day, right? Like who's commuting more than 90 minutes one way? Like, let's look at that analysis. Now, I did the first analysis and then did the second one as a robustness check, right? To see would it change my decision making. From a standpoint of throwing out data, you have to be super careful. You have to see how it changes your analysis. What does it do? How does it do all those things? It is a second step. For my purposes, for homework, I'll tell you if I want something removed, right? But if you see something worth pursuing and you take me down that rabbit hole, feel free to talk to me about why you did it. The thing with me, and I will tell you this, I want you to explore. I want you to try. Justify what you're doing. Okay? If you justify what you've done, if you explain it to me, you are always safe. That will be the thing I will tell you. Tell me why you did something, and I promise you, you will be on the safe side of things. And the reason I say it that way, you all are used to math questions where 2 plus 2 equals 4, right? You all getting ready to walk into the world where I'm giving you, you put 10 statisticians in the room, you're going to get 9 different ways to do something. And the 2 that gave you the same way went to grad school together. Okay. You're going to draw the same conclusion, but you're going to get there slightly different ways. It's not 2 plus 2 equals 4 anymore, especially by the time we get to the end of the semester. All right. So that's part of the reason I'm telling you, take me down your path, justify, show me what you tried. There's going to be times where there's right code, but how you got there is going to be a lot of different ways. All right. That's part of the reason we say this is about critical thinking and problem solving. All right. Anybody have any other questions? What y'all think? Is this going to be useful?
Yeah, definitely.
Yes.
Definitely.
Uh,
For
sure.
I'm gonna watch this like 30 times.
Same here.
every week, this is what it is. Okay. I promise you that. This is what it is. Don't be, and going back to the point, don't be, if you can't make it, that's okay. I record it. I do those type of things. I appreciate y'all being as interactive as this group has been. Okay. I try and make them useful. I try and make them targeted. I try and do these type of things. I am reshooting. Let me just be upfront with you too. I am reshooting a bunch of videos associated with this class. So I'm trying to get modules up as quick as I possibly can. Okay. You'll see starting in module 2. Oh, and that was the other thing I was going to show y'all real fast. Apologize. Give me just a little bit of grace here, y'all. So starting in module 2. Module 2, you'll see it goes under the West Virginia Buddha logo because it goes under the private repo. Lovingly, you all are paying for this class. I don't want to put all your notes up for free. Like, I don't like putting that first version up, but I can't start you all so far behind where everybody's got to get registered for GitHub and everything like that, right? So I have to get you started with something. So all your notes go up behind the West Virginia Buddha GitHub page. What you will see and what you will start seeing some older videos of me. I do not look like this. I look a little bit different. I'll put it that way. But there's a light board. I'm able to draw on a board. I'm able to do some things. The videos are the most important part. You can go through the notes. You will see some stuff where we get into some heavy math. Where is it? Where I get into like calculus derivations. I'm not testing you on the calculus. I'll never ask you about the calculus. I don't care about the calculus. Some of these notes are for you down the line if you get into that type of stuff. I even tell you it's informational only. Okay? Watch some of the videos that go with it if you have time, but understand what I want out of this is extremely applied and extremely hands-on for you. Okay? This isn't a calculus class. This is about how do we solve problems with technology. Some of this stuff is to make sure you know. Out of these two things, focus more on the applied example, okay? If you see a ton of equations, understand there's probably a video that goes real short into that, and then we're jumping to the applied example. So I would focus on the videos and understand when we get to the collaborate, we're going to get real hands-on about it, all right? Y'all with me on that?
Yes.
Yep.
And remember, I'm always here for you. If you have a question, if you have a concern, I got you. Just reach out to me, all right?
Thank you.
Thank you.
Thank you very much. This was super helpful.
Y'all have a great week. If you need anything, yell at me, okay?
Thank you.
Thank you.
See ya.
You too.